as we have this online platform, and as it is not always possible to discuss the things, so to understand that how much you have uh, the grasp on the concept, I shall give you two different type of assignment. Maybe some of you have learned from your seniors that what are these two, but if you don't, let me explain. So one of the assignment, these two assignments you may submit, well, I mean in November, or first week of November, second week of November. First week of November is fine. So the point is that once I finish the syllabus, or you can start your assignment right now. I mean, it will take a little, it may take a little time. That whatever you have read, whatever topic you have read, you will make questions, right? You need to make 20 questions. Now, these questions is not expected to it is not expected that you will copy from somewhere these questions, right? Now, if let's say, let me put 10 marks on the question, this assignment, then if someone of you have copied everything from other books, so I mean, please remember that as you have access to Google and all these things, I also have this access, right? So if you just copy the questions exactly from these books or anything, like a problem from a paper, and this is in the newsletter or something, I encourage you not to do that. I mean, the point is not that you, whether you have read all the questions from all the books or not, like that. It is the, I just want to see that how do you give the importance to the problems that you are dealing with these subjects. Like for instance, when you read the total electronic spectrum, what are the things that you feel is more important than the other part? So what are the questions? Yes, you can say that, ma'am, is it possible to make questions that are not already in the book? No, this is not possible, I understand. But see, I mean, if you try your best and if you write it from your concept, it will be little different, and that I can understand, that whether you have just copied it from somewhere or you have tried to understand. Because I shall give the importance to the question, as well as that from where you are doing the questions and all these things. So is it understandable to you, or if you have any question regarding that, please let me know. Or if you feel that okay, you will think and next day you will ask me the question, that is also fine. So let me know. I mean, at least one or two of you just make clear that whether I could make the point or not. No, you don't need to write the answer. Any more questions?
Ma'am, when do we have to submit this? First week of November? Ma'am, am I audible?
So you don't need any more clarification. Yes, 20 questions is fine. I mean, till November with this D block, this bonding, and then electronic spectra, and then we'll do the reaction mechanism a bit. So 20 question is fine. So if you feel, all of you feel that it is 15 question, it is fine. I mean, I don't have any problem. So, shall I move to the next to explanation of the next assignment, or okay? So the next assignment, it is a little bit a different type, or it may not take much time, but the concept is that, so you have learned the bonding and the electronic spectra, and then you have this reaction kinetics, fine. So once you finish these chapters, or again you can write now, so you may find some journals, right? So you have to look for a journal. So you have to look for a journal. So let me first explain that what you need to do. So you take a journal, and then you pick up a problem. The problem must be related to whatever you have read. It may be very easy journal. It is not that you have to pick up a very difficult problem that you do not understand or anything. So you need to pick up a journal, and then you have to present the journal by either by video. I mean, you have to record it. You have to send it to me, and you can upload it in the WLAN as well. The main point is that you cannot cross 5 minutes. I mean, if you cross five, the first thing is that you have to make the presentation in 5 minutes, right? So the 5 minutes presentation, whatever you can do. So last year people have done it. I'm explicitly saying it because I want that you do it singly. I mean, but if you insist, you can go with two in a group. In that case, you have to make the presentation in that way. I mean, someone will stop somewhere, and all this is it is not that online presentation. It is, you have to do a this video, and then you have to send it to me. But you have to maintain the time limit. So if it is for two persons, then it will be for 10 minutes. The most important point is this choice of the journal. So this choice of the journal, I may help you, but the initiation must be with yours. Like if you just send me, if you pick up five journals, it is take very simple problems. Like if you go to the go and search journal, you will find that on Taylor distortion only you will get too many journals. So to pick up the very basic problem, like a little bit of spectra. Let's say there are a different type of ligands of a nickel metal. Let's say it's metal nickel, and then you have three ligands, and then the spectra is changing. If the paper contains too many other things, biological, this things, you may ignore if you choose a journal like this. What you have to do, uh, if you do it in the group as well as if you do it in the singly, in that case, if you have any confusion, if you choose five journals and if you send it to me, I can tell that pick this one up. That much help I shall do to pick up the problem. But please don't go to a beyond the subject of this class. It's not that I want you to explain that the nanoparticle generation with application in this something very big. No, just the problems from these, whatever you are taught in the class, very basic things, right? And a little bit, I mean, not all the basic, it is not the, even if you choose a paper where is a 1938 paper, let's say, and where people have tried to make tried to understand what Jantala theorem, if you can present it well, it's welcome, it's not a problem. But basic problem, a little bit of application, and then this explanation within 5 minutes. So now let me know. Uh, again, this one you can submit before mid sem. Sorry, before NSEN. Any day before NSEN. So is it clear? Quick, then I shall start this reaction mechanism. Okay. So I think what yes, PowerPoint any presentation. PowerPoint presentation is all welcome. I mean video, I mean PowerPoint I meant. Okay, so let me start. So what we'll do, try to understand today is that, so you all of you know that this application like catalysis and these all these things happen. So why transition metals are so important, because it is a huge application in the catalysis and all these things. So what actually catalysis means, I mean from class 7 or class 6 you can define that catalysis is a thing that helps in to in a reaction to I mean to a little bit of I mean the speed of the reaction changes. I mean it's not that the catalysis make a thermodynamically impossible reaction possible, but when a reaction is thermodynamically possible, then catalysis actually uh, helps it kinetically, so it goes to the so you are all of you are well acquainted with the terms that activation energy and all these things you are acquainted with. So when and in organic chemistry you all have read all these things. So let us see this reaction mechanism in the perspective of the inorganic chemistry. So inorganic chemistry means the transition metal chemistry. That is the main thing here in this course. And as you have now a clear idea about the bonding in case of these transition metal complexes, so it is definitely associated with that this bonding. I mean, so reaction mechanism will specifically, I mean most importantly, the reaction mechanism in case of a inorganic metal complexes is the ligand substitution. So let us write the key words for this. So today is probably day 17. I do not remember. So ligand substitution reaction. Now, if you have, let's say, these reaction, let's say whatever you have, anything can be there. So this is called ligand substitution reaction, right? So in this ligand substitution reaction, we um, take a metal complex, and how fast or how uh, quickly this ligand substitution reaction takes place, that uh, depend on the electronic configuration of the particular metal, and this electronic configuration in most of the cases is the is associated with the oxidation state of the metal, as well as the bonding strength and the how strong the bond between these two, this NCl. Because what is happening, Very simply, there is a MCl bond, and this MCl bond is breaking, and then this another new bond is forming, right? So this is the main thing. So if you now see that what is the, so what are the things that we look for? So first thing that will is the rate of the reaction, right? So rate of the reaction, where it is depends on number one, configuration, or you can say the oxidation number, oxidation state, sorry. And another thing that we will discuss, the structure of the complex. Why? A bit, let me explain. Like, if structure of the complex, if you see that if you have a metal in octahedral geometry, then the difference between this T2G and EG, and if you have a this tetrahedral, then the difference between the T2G and EG is very small. So it is all that energy is very much associated, and this is one of the point, that structure of the complex. And why? Because once you have a different structure, you have a electronic this mm, let's say this the orbitals are uh, I mean, orbitals are uh, oriented in such a way that when some other ligands approach to it, whether it can overlap with a vacant orbital, or it is competing with another orbital. Because if you just very simply, I just am just telling that if you have a orbital like this, and if you have one of these, let's say this is metal, and if one of the ligand is from L1 is from this side, then if one L2 comes from this side, then this L2 wants to make the new bond from here so that it goes out, but it has a just a minute. Sorry. Okay, so it has to compete with this another ligand, and also, so it depends on the electronic configuration, structure of the complex, and the nature of the ligand. So the ligand, so incoming as well as spectator. So these terms are very important. So what a spectator ligand, like here, if you just look at this, then here water is the spectator ligand, because there is no change that has changed to this water molecule, and in most probable case the geometry of the molecule remain as such. I mean, this M water whole 5 remain as such, right? So this is, and the incoming ligand here is the I minus. So nucleophilic, I mean, we'll see that we will see it as a nucleophilic substitution reaction. As it is a nucleophilic substitution reaction, so the incoming ligand also has a part to say. And there are mechanisms that actually determines whether how much does it depend on the the presence of the incoming ligand. I mean, even if incoming ligand has a has different nucleophilicity, but whether it is yeah, I mean participating in the rate determining step or not, that actually decides that how much that incoming ligand is affecting the system. Okay, so now let me show you one thing. It is all of you know it, but let me show you that if we take this is a potential energy, and if this is a reaction coordinate, then then you know that their reaction is always goes through reaction always go through in active. So you need to go through this activation. হ্যাঁ আমি ক্লাসে আছি বলো so this is the activation energy. So if is the start. Okay, starting material I shall not write. So what I shall write? So if it is mln and you have this x, and if you have y, you have y is the thing, and then you will have mln y and this x. Now you have to overcome this barrier of this activation energy, and you will find the light bulb. But what happens? What are the possibilities? First, let us understand that what are the possibilities. So, what are the possibilities? If you have m ln x and your reaction is final reaction is m ln x plus y, then m ln y plus x. So this is the final. So what are the possibility? Possibility one is that m ln x goes to m ln plus x, and then y comes, and it is m ln y plus x. And the second possibility is that m ln x y comes m ln x y minus x m ln y plus x. So, in principle, these two possibilities are there, and this is called dissociative mechanism, and this is called associative mechanism. So from the name you are quite sure that what is dissociative and what is associative, right? Now there is another form. So I shall explain it. That is what is the name? This dissociative, associative, and between the interchange. Let me see. I mean, I just forgot. Okay. I shall come to this. So these are the three. Let me first show you. Then there is a concept of microscopic reversibility. So this term is a little bit important, but you will understand it. Reversibility. Now, if I go for dissociative, then what? How shall I write? So, Let me first draw it in that way. So M L N X M L N X Y M L N Y X. Now, so there are two potential barrier. One is from MLN X to breaking of these MLN to X, and then association of. So this part is dissociative mechanism is dissociative. Okay, mechanism is dissociative, but under this part is dissociation. I am writing in different color. Okay, so this part is dissociation and this part is association. Is it clear? This one you have to make be clear, then it will be. I shall proceed. Is it clear? Yes. Okay.
Yes, ma'am.
Now, so this is dissociation part is association. Now here first you try to understand the microscopic reversibility. So what does it mean? Now you see when you have something at this point, when you have something at this point, so this point has this energy, let's say this point energy and this point energy in both the side, these two energy are same. So if M, ln, X and Y, all the species are there in the solution, then for a MLN, XY, all of them are there. So going to this part and going to this part has the same probability, and this is called this. I mean, if you just like in a hill, there is a valley, so you can. So generally, what we do generally, let's say we went some tourist spot and we have started from here, so we are here, and then some people prefer to come through these, and some people prefer to come to the other side and go back. Or sometimes what happens that some people when they are coming over there, they are feeling tired or something, even if they have some the 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 plan that they will go through this one, but still they go back, right? So all these things can happen, and it is understandable from that at this put energy there is this uh, possibility of these two. But yes, reaction do happen, and for that reason sometimes what we do that we do change the conditions of the reaction so that it goes to the uh, uh, the, the the final product, final desired product. Final product is nothing for them. I mean, whatever happens at the end, that is the final product for a reaction. But it is from our perspective that we say that this is a final product because we desired that product, right? So this is the dissociative. So here, if I, okay, I shall come back another ways. And then if you have a associative mechanism, then what will happen? So you will have a coordinate like this. This is potential energy, and this is reaction coordinate, and you have a million x, you have a million x and y, and you have a million y plus x. So this is for associative mechanism. And again, this part here is associative, associated, and dissociation. Here, and this part is dissociation. So now what happens that the third one is the Interchange mechanism. I wrote interchange, right? Now here what happens, it is, I am coming, I mean let me draw and then I shall come. Reaction. So what happens, m ln x, and then x comes from this. Now you can tell me that, so this is here. Now you just see that for associative mechanism, we have written it like ml n xy. But for interchange mechanism, we are writing is at this. So what is the difference? The difference is that for an associative mechanism, when we are telling you as it is an associative mechanism, then this is the intermediate, and it is long lived in terms of reaction mechanism. Intermediate is long lived. Is Now this long lived word doesn't have meaning until and unless you give some reference. So what is the reference? That you can trap the intermediate either materially, I mean by spectroscopy or something, or you can uh, only spectroscopically you can trap see the intermediate difference between, or there is any change in the reaction, not reaction, the structural change, like structural change, like change in geometry. Now, but all these things doesn't happen here. But then why I am telling that it is associated? Because then other parameters that decides that whether the rate determining step depends on the concentration of the incoming ligand or not. So there is the concept of rate determining step. So there is a concept of rate determining step, and that gives you uh, the idea of this. What is the why it is the dissociatively associative or something. I'm coming. So here it is the association, association, and this is the dissociation. So now if I now draw, so
Excuse me, ma'am.
how does it happen?
Excuse me,
So
ma'am.
dissociative path generally is D. Now dissociative can be DA or it can be DD. So how does it happen? So association is the rate determining. So if it is like this, so this is the rate determining step, and if it is like this, Similarly, let's see. Associative pathway, then AA or AD. Right? And this is area, then enter, then I. It could be ID, it could be IA. Please see the drawing from the book. You can find it any standard book. And if there is any, so is it okay? All these things. So if there is any question, please let me know. What? Isha, what? Probably not. No, I cannot hear you. I do not know. I have to ask uh, this system administrator what is happening, because earlier I used to listen to. Yes, okay. You just let me know. Write in chat box. Let me see if I can give you some permission. Okay, I have all muted. I cannot make you this. I cannot give you the this all mutation. I cannot do undo anything. So please let me know that whether you can you have understood. So Shamrik has written yes. So anybody else? Please write in chat box. Yes, it is transition state. It is transition. Absolutely. I have not used the term. No, the reaction coordinate is not a single hill graph. You see, it is not always the single hill graph, because what is happening recently, I mean, sometimes see the every day the scenario is changing. So when we in let's say last 20 years in the before 20 years you could not trap some of the reaction intermediate, because you do not have that much of sophistication. Yes, that I shall come, Kundan. That ligand, that depends on this reaction. I mean, on what it is depending on that. This ligand instruction always say that it depends on this. I mean, when the rate of the reaction we will find, then we will see that whether it is depending on the uh, first one is the incoming. So there is a difference between the incoming and the spectator. So how does it happen? So if it is incoming ligand, then that incoming ligand should be it is easy to check whether it is dependent on the incoming ligand or not, and depending on that we have decided that dissociatively associated or associatively dissociated, all these things. Like let me tell you. So these two are very different, incoming and spectator. So how does spectator affect, that we will read very a little bit detailed in the trans effect, because spectator ligand does not you would not understand it from the rate of the reaction, because it is there in the uh, complex. So if the total complex is participating in the rate determining step, the concentration of the starting material or substrate, then you cannot differentiate between the spectator ligands or this one. I shall come to the main point, this inert and lability concept I'm coming. And the incoming ligand, again, it is very easily understandable from the rate of the reaction, that the reaction incoming, whether it has a dependence or not, that if you just change, let's say you want to you have a bromine displacement and you are changing it to the iodine displacement. If you see that the keeping all other things similar, all the concentration of substrate and the reaction conditions and all of these things, if you just keep constant, and if you change from bromine to iodine, and if the reaction is facile, I mean it is more easy, then you can easily say that it depends on the iodine. But if you see that is the point, like if you have, let's say, ligand bromine and iodine, and if you choose, if you just go that what is the nucleophilicity of that particular incoming ligand, and if it happens that this incoming ligand, one of them is highly nucleophilic than the second one, then also in some reaction that has no meaning, because the incoming ligand is not participating in the rate determining step. Some point, I think, is it clear? Some points. Spectator, I shall come. Okay. Now, so when we are telling all these things, so from here, one very important thing then that I have not missed, but maybe, I mean, if you find some standard book, it has been discussed earlier, and I was just showing it, and so I forgot. But it's not that I'm not coming. So, two very important term you will find throughout this reaction mechanism. One is inert and one is labile. And this inert is, sometimes some books prefer that non-labile. So what does it happen? Like if you take a reaction, so how do you know? So if you take, let's say, as far I remember, so it may not be, it may be just an example. Maybe I'm not very sure about. I'm just showing it. So you are taking water exchange reaction. So water exchange. So what will happen? Because in that case, what Kundan or someone Kundan has asked, that you are not taking the strength of this metal ligand. I mean the ligand, the outgoing ligand and the incoming ligand are the same. 2 plus water, and if you take this one, you have a question, right? This one, and you will find all these things application here in all the cases, spectra, and then, but what we have told that cobalt 3 plus is much more stable. So this one probably, please, I'm not very, probably this is 13 times faster. Whether this one or I do not remember, but let me try. Is way faster. I mean, the reaction is faster. So this inertness and this lability is a little bit of comparative, but the labile complexes are generally what they go to the product. I mean, they do take part in the reaction, ligand substitution reaction very easily, and the inert complexes are not that much, and that also in the it is compared with the time scale of 1 minute. I mean, if it can have a lifetime of this 1 minute, then we can say this is an inert reaction. Here, one important thing, maybe today, what is the time? Today I shall not get the term time. So this inert and debility is all associated with kinetic term. Kinetic term. Don't mix it with thermodynamic term. Like, let's say you have a m ln x plus y, and you have the product. Whether you will get the product, that thermodynamics say. So it is a quite easy thermodynamically feasible reaction that might take 28 days to complete. So what we'll see that this is the inert complex. But it does not mean that it is thermodynamically not feasible. It is feasible, but it is inert complex, so it is taking time. But the labile complex is quite easily it goes. And this lability, I mean inertness, very simply, inert complexes are generally small cations, metal cations, and then D3, then high spin D6, high spin D3 to D6. All these are inert complexes, and this is related to LFAC, it is related to chelate effect, like FeH2O whole 6. If you just take this, the lability is higher than Fe by will whole 3 2 plus. So I think let me stop here, and this is quite a little almost introduction to the reaction kinetics, and you have understood, right? So if you have any question, let me know quickly, because otherwise I have to explain so many things. You can consult any standard book for this part, and please do. I mean, then it will be easier for you also to interact. If you don't have any question, I can.